A map is a print. It shows you how to travel from one place to another. It shows you what kinds of roads you'll be traveling on. It shows you what sort of countryside you'll be traveling across, whether you'll be crossing mountains or rivers. It shows you with symbols where airports, churches, and hospitals are located. It shows historical sites and state parks. And it shows you how far you must travel between points. Most maps also include a legend that explains the different symbols used on the map. Well, you use prints around your home all the time. You use them to build models, to operate power tools, to change a tire, to put together a bicycle. All of these prints use pictures and symbols. Now, these prints are often called drawings. For the sake of consistency in this tape, we'll refer to prints throughout the tape. Regardless of what they're called, prints accomplish a couple of important objectives. They provide you the information that allows you to figure out how to do something, whether it's building a ship or making your way across country, or they provide the information that enables you to figure out how something works, whether it's a vacuum cleaner or the furnace in your home. In this tape, we're going to be primarily concerned with prints that represent mechanical systems or machines. These prints may be of several types, such as blueprints, schematics, or elevations. All of these types of prints have the same objectives. They enable us to figure out how something works or how to do something. They differ only in how they present the subject. This presentation can be made pictorially, that is, by use of pictures, as with model airplane instructions. Or the presentation can be made using symbolic representation, that is, by using symbols to represent the various parts that make up the machine or system. Why would we want to use symbols? It would seem that pictures would be easier to understand. Well, to start with, we're pretty familiar with the idea of using symbols. We use them in everyday life for a lot of different reasons. For example, we use the symbols on the map to represent churches or airports. We use symbols to train athletes, and we use symbols to control the traffic on our streets. We use these symbols because it is easier and more efficient to use them than it is to draw a picture or write something out. Another advantage to the use of symbols is that they enable us to represent something that is very large and complicated on one or just a few pages of paper. To reduce the picture of a large turbine generator to a size that could be used on a one-page print of a power plant system would result in a shapeless blob. But a symbol like this can be easily used and can have the same meaning. Symbols are the language of most mechanical prints. In our spoken language, we use words that have generally accepted meanings, and we string them together to form sentences that communicate information. Just so, we use symbols that have generally accepted meanings, and we connect them together in various ways to form prints that communicate information. Another comparison with our written language exposed one of the problems involved in the language of symbols. It's a pretty true statement to say that the major language used in the United States is English. But various regions in the United States speak English in different ways and with different accents. And to truly understand what's being said, you have to know where the person comes from. In reading prints, there are many symbols that have almost universal meaning. This, for example, is a valve on almost any print. But just as different areas use the English language differently, different manufacturers use different sets of standard symbols. Plants and factories also use their own sets of symbols in their system descriptions. An example of this variety of symbols is that these symbols all represent a normally open gate valve. Because there's no one set of standard symbols used, manufacturers and plants have to provide a chart indicating the language that they use on their prints. It's very important that you find and use this chart or legend whenever you read a print. Usually, a manufacturer will use a standard set of symbols throughout his prints, and a plant will use a standard set throughout its prints. When you have found the correct legend for a print, you can then read that print. In this tape, we're going to discuss three very specific types of prints. These are the mechanical prints that you are most likely to run into in your day-to-day work around the plant. First, we're going to discuss piping system prints. Very few plants can operate without piping to carry various fluids from one area to another. Well, whatever the purpose of the fluid is, you'll need pipes to transport it. As long as you have piping systems to do this, you'll need to know how to read a piping print. If you can properly read a piping print, you'll have a solid understanding of just how that particular system works. You'll know where the fluid comes from and where it goes to. You'll also be able to figure out possible solutions for any problems that you might encounter with that system. Now, the second type of print we'll discuss is the fluid power print. A lot of the mechanical devices in your plant are probably operated by hydraulic or pneumatic systems. A hydraulic system uses a hydraulic fluid, like oil, to move a device such as a lever or arm. A forklift truck is a good example of using hydraulics, in this case for lifting and carrying heavy loads. A pneumatic system uses air in much the same way that a hydraulic system uses oil. In your plant, you may have air-operated valves. The dampers in your ventilation system may be air-operated, and you probably use various air-operated tools. Perhaps the best-known example of a fluid power system is actually a combination of hydraulics and pneumatics. The lift at your local garage is a fluid power system. It uses pressurized air to put pressure in an oil reservoir. The pressurized oil then pushes up the large piston that raises the ramp. When the air pressure is bled off, the ramp slowly lowers. The third type of print we're going to cover is the equipment print. Equipment prints come in several varieties. There are prints that explain how to assemble a machine, how to lubricate it, how to maintain it, and how to install it. We'll be concerned with two basic types of equipment prints called assembly drawings and detail drawings. Both of these prints require an understanding of how the parts of a machine are fastened together. So we'll spend some time looking at the various methods of fastening parts together. Well, at this point, let's stop for a minute and review what we've covered. We know that prints are used to communicate information. We know that prints can come in a variety of types and under various names. They have in common the use of symbols and pictures to show something. The use of pictures results in pictorial prints. The use of symbols results in symbolic representation. The use of symbols has several advantages. These include increased clarity in a print, getting around the problem of large size differences in a print, and fairly standardized meanings for the symbols. We also discussed the fact that standard sets of symbols will vary from manufacturer to manufacturer and from plant to plant, and that you have to find the legend that explains the symbols for a particular print. The purpose of this tape is to introduce you to three basic and very common types of drawings that you are likely to be using fairly often: the piping print, the fluid power print, and the machine or equipment print. Well, for right now, let's stop the tape and review Section 1 in your text. In the next segment, we'll move into an introduction to piping system prints. At this point, we've discussed prints in general and why we frequently use symbols to represent components on prints. Now let's take a look at piping system prints in particular. Explore the symbols used and see how they're connected together to represent a piping system. Piping prints are perhaps the most common type of print that you'll use in your day-to-day work, often called P&I prints for piping and instrumentation. They illustrate piping systems. A piping system is simply a transportation system for a fluid, that is a gas or a liquid. The job of the piping system is to get that fluid from one location in your plant to another. A pipe by itself is not a complete system. Just as a truck driver must be able to change directions to reach his destination, a piping system must be able to change directions. Just as the truck driver has limits on how fast it can travel, a piping system must be able to control the speed of the fluid it is carrying. A piping system uses fittings to control the direction of flow. To control flow rate or speed of the fluid, a piping system uses valves. All we need to complete a piping system is a device to provide the force that moves the fluid. This would be a pump or a compressor. We won't be discussing pumps or compressors or the many other components that you'll find in a piping print. The symbols for many of them are listed in your text. In this tape segment, we will cover piping, valves, and fittings, the skeleton of the piping system. A piping system can be represented in one of two common methods, the double-line print and the single-line print. A double-line print is a pictorial representation. That is, it uses pictures of the piping and components in the system. It is easier to follow than a symbolic representation. The major disadvantage of a pictorial print is that it takes up a lot of space. A large or complex system cannot be easily drawn on one page or sheet of paper. Double-line prints are often seen as an insert or a side drawing on a symbolic print. This insert can help to clarify a confusing point or area in the system. The single-line print is the type that you will normally be using. It's not as easy to follow at first, but in the long run, it's more practical to use. The single-line print uses symbols to represent the piping and components. This is a single-line print of the same system that you just saw as a double-line print. You can see that the single line is much easier to draw, but that a basic understanding of piping symbols is necessary before you can start reading it. Well, let's start with the symbols that are used to represent the piping itself. This is a print of a portion of a piping system. We'll use it throughout this segment to help explain the points we'll be covering. We'll use different colors for the various components to make things more clear. But of course, you won't find real piping system components in the colors we'll be using. We'll start with just the pipes, then add the other components as we go along. It would be difficult to tell much about a piping system with just a print like this, but if we use the legend that accompanies the print, we can learn a great deal about the pipes themselves. For instance, almost any piping system will have pipes of different size and different functions. This is the legend for this print. You can see that this thick line indicates a 5-inch pipe. This dashed line indicates an instrument line. And these various symbols represent various components in the system. Remember that this is the legend for this print only, and that you must use the legend that goes with a particular print. One of the important points to observe in a legend is the way in which the pipes are shown to join or to cross over each other without joining. In this method, the non-joining line stops on one side and starts on the other, never touching the line that it does not join. There are several other methods of doing this. This is just one. Your text shows some of the others. Another key to look for is how the direction of flow in the system is indicated. These are flow arrows. Once you've found the legend, you can tell several things about this system. For example, the legend shows that these are 5-inch pipes. These are 3-inch pipes. 1-inch pipes, a pipe that does not join the system, and instrument lines. Knowing that these are instrument lines, you could expect to find some sort of instrument, such as a pressure gauge or temperature indicator at the end of the line. Apart from the size of the pipes and the function of some of the pipes, there's not much more information that can be obtained from this print. So let's take the next step and put in the joints and fittings that connect the pipes together. The connectors that connect the pieces of piping are called fittings. The actual joints between the pieces are called just that, joints. Now, let's look at some of the common fittings and the way they and the system components are joined into the system. There are 3 common methods of joining parts of a pipe system together. Your text presents 2 other methods, but The three we will discuss are the threaded joint, the flanged joint, and the welded joint. This is a valve with a threaded joint. A threaded joint simply has threads like a bolt or a nut, and the parts are threaded together. This type of joint is used primarily for small piping of 6 inches or less. This is the symbol for a threaded joint, a single short line that crosses the pipeline at a 90-degree angle. This is a flanged joint. Each face of the joint is spread out into a flange, and the two flanges are bolted together, usually with a gasket between them to prevent leakage. The symbol for a flanged joint is like a double-threaded joint with 2 vertical lines crossing the pipeline. This is a welded joint. The 2 pieces are welded directly together. This is a more permanent joint than the threaded or flanged joints. This is the symbol for a welded joint, simply an X on the pipeline. Threaded, flanged, and welded joints are the most common joints you'll see. Now, let's take a look at the most common fittings. A fitting is used to change the direction of the piping, to change the size of the piping, and to provide branch connections that bring other pipes into the system. The most common fittings are reducers, couplings, elbows, T's, and crosses. This is a reducer and its symbol. The reducer is used to join 2 pipes of different sizes. This is a coupling, used simply to connect 2 pieces of pipe together in a straight line. This is an elbow. An elbow is used to change the direction of the piping. There are a large variety of elbows that change the direction by almost any angle, but the most common elbows are the 90-degree elbow and the 45-degree elbow. An elbow fitting will also have 3 symbols: threaded, flanged, and welded. This is a T fitting. A T fitting allows a branch connection into the system. This means that another pipe is joining the system. There are 3 joints on any T fitting, and you can see them represented here. This representation of the T fitting brings us to a second method of showing piping size that does not depend on thick or thin lines. This is a 4-inch by 3-inch by 2-inch T fitting. That means that the left pipe is a 4-inch pipe, the right pipe is a 3-inch pipe, and the branch pipe is a 2-inch pipe. If the main pipe did not change size here, the T would be described as a 4 by 4 by 2 T. The last number is always the branch connection. The last common fitting we'll discuss is the cross fitting. This is simply a fitting that joins 4 pipe ends together. Again, the size of each pipe can be easily shown by putting it next to the pipe. All right, we've connected air pipes together and used fittings to change piping directions and add branch pipes. Now, let's add the valves to our system to allow for control of the flow through the pipes. We'll cover the 3 most common valves here, but you must be aware that any piping print may have many more valves symbolized on it. Just make sure that you check that legend. This is a gate valve. A gate valve is used to stop and start flow through a section of piping. Gate valves are normally made to operate in a fully open or fully closed position. These are common gate valve symbols. The symbol on the left indicates a gate valve that is normally left open in the system. The symbol on the right indicates a gate valve that's normally closed. Gate valves have several methods of operation, including manual or motor-operated. On this print, we have normally open gate valves, normally closed gate valves, and normally open motor-operated gate valves. The M in the block indicates a motor operator. This is a globe valve. Globe valves are used to control the flow rate through a piping system. These are some of the more common symbols for a globe valve. Again, the solid colored symbol is a normally closed valve. The clear symbol indicates a normally open valve. When we put the globe valves on the print, you can see where the flow rate is controlled in this piping system. This is a check valve. This cutaway view shows how the valve operates. A check valve operates to allow flow only in one direction. If the flow starts to go in the other direction, the check valve closes and stops the flow. A check valve symbol may be accompanied by a flow arrow, or indication of some sort that shows which way the valve will allow flow. On this symbol, the slanted line indicates the disc inside the valve, so the symbol itself indicates that flow is from left to right. On our print, you can see that the check valve symbols can help us determine how a system operates by showing which way the fluid flows. Well, our piping print is beginning to take shape now. We have the pipes to transport the fluid, the valves to control the flow. We need to add a couple of pumps here to provide the force to push the fluid through the system, a couple of strainers to filter the fluid, instruments to indicate temperatures and pressures, a reducer here to step down the size of the pipe for a sampling line, and we have a pretty representative system. Piping, fittings, joints, and valves are common to all piping systems. If you can recognize them when you look at a piping print, you're well on your way to being able to read and understand that print. The various other components in a piping system are many and varied. A lot of them are shown in your text. If you use the legend that accompanies the piping print and the information in your text and in this tape segment, you'll have few problems in reading a simple piping print. For now, stop the tape and review section 2 in your text. A fluid power system is a system that uses a fluid to accomplish work. This fluid can be either air or liquid. If the fluid is air, the system is called a pneumatic system. If the fluid is a liquid, the system is called a hydraulic system. Although hydraulic and pneumatic systems use different components, they're both shown on prints in similar ways. Where different symbols are used, we'll point them out when we go through some typical system prints. Before examining any prints in detail, though, let's take a minute to discuss the major differences between these two types of systems. The basic differences that require different equipment for the two types of fluids are explained through the ideas of diffusibility and compressibility. Now, those are long words with pretty simple meanings. Diffusion is the mixing up of the molecules of one fluid with another fluid. For instance, if you open the valve at the top of this gas cylinder, the gas would escape and mix with the air. This is diffusion. If, however, you take the lid off this container of oil, the oil won't go anywhere. It will not diffuse into the air. Because of this difference, the methods of storing the working fluid in a fluid power system are going to be different for pneumatic and hydraulic systems. In a pneumatic system, the air has to be stored in a closed container so that it will not escape by diffusion. The container is called a receiver. A receiver also allows the air to be stored under pressure. In a hydraulic system, the situation is a little different. Since liquids don't readily diffuse into the air, they can be stored in either open or closed containers called reservoirs. The two fluids are also different in terms of compressibility. Basically, a liquid will not compress, while a gas will. To explain this, imagine a container filled with a liquid. Pick a piece of solid material, such as a block of steel, that exactly fits the top of the container, and then push down on it. The liquid will not compress. It will not be squeezed into a smaller area. If the fluid in the container is a gas, however, and you apply enough force to it, you can compress it into a smaller space. This is all that a cylinder of compressed gas is, gas that has been forced into a smaller space. What this means in fluid power systems is that hydraulic reservoirs tend to be much larger than pneumatic receivers. Since liquids aren't compressible, a reservoir must be large enough to store all the liquid in the system. Air, on the other hand, is compressible, so it can be stored under pressure in a relatively small receiver. It's this stored pressure that enables the air in a pneumatic system to do work. As air is used and the amount of pressure in the receiver is reduced, the system's compressor starts up and recharges the receiver. Now that we know the major differences between the two fluids used in fluid power systems, we're ready to look at some system prints. We'll use this print of a simple hydraulic system to start with. This system has a reservoir containing hydraulic fluid, a pump, a pressure regulating valve, a directional control valve, and an actuator, a piston and cylinder that are used to perform some sort of work. It's important to note that although plant prints often contain symbols that represent both piping and tubing, the interconnecting lines on fluid power system prints usually represent tubing rather than piping. The objective of a typical fluid power print is to show not only the tubing that makes up the system, but also the flow paths that result in the fluid accomplishing some sort of work. Frequently, these drawings are also called schematics. And just as with piping system prints, fluid power schematics will also have a legend to identify system components, lines, and flow paths. On this legend, take note that the flow arrows are different for pneumatic and hydraulic systems. The pneumatic flow arrows are outlined, while the hydraulic arrows are solid. In both cases, they're used to indicate the direction of fluid flow. This is the symbol for a hydraulic pump, a vented hydraulic reservoir, and a strainer or filter. Here's the symbol for a pressure relief valve, a flow control valve, and a directional control valve. Many fluid power systems use flexible hoses, identified by this symbol, in addition to or in place of tubing. Flexible hoses are often used when a connection must be made to a piece of equipment that moves or vibrates as it operates. While there are many other symbols used in fluid power system prints, for now, let's look at how this system operates. When the pump is running, hydraulic fluid is pumped from the reservoir to two branches of the system. One branch leads to the directional control valve. The other branch leads to a pressure relief valve. The relief valve is used to maintain proper operating pressure in the system. The arrow inside the box indicates direction of flow. The dashes on the symbol represent a pressure sensing line. It puts the pressure developed at the discharge of the pump on top of a spring-loaded valving mechanism. When pump pressure exceeds a predetermined value, the valving mechanism, such as a poppet or spool, is pushed down, opening up a passageway inside the valve. Some of the hydraulic fluid then flows through the valve and back to the reservoir, thereby reducing system pressure. This symbol, attached to the valve, indicates a return line to the reservoir. When system pressure becomes less than the spring tension, the spring closes the valve, increasing system pressure. The relief valve will open or close as necessary to keep pressure constant throughout the system. In this way, fluid at the proper pressure will be supplied to the next component in this system, the directional control valve. This directional control valve symbol illustrates the possible flow paths within the valve. The directional control valve controls fluid flow in more than one direction, and it can change the path of fluid flow. This valve symbol also shows a closed position in which there is no fluid flow. The best way to understand directional control valve operation is to look at it in relation to actuator operation. The actuator is here. It's basically a piston inside a cylinder that's filled with hydraulic fluid. For the piston to move downward, two things have to happen. First, there has to be a source of hydraulic fluid pushing down on top of the piston. And second, there has to be a flow path for the fluid underneath the piston to leave the actuator. These flow paths are shown in the directional control valve symbol. Incoming hydraulic fluid is pumped through this part of the valve and into the top of the actuator. As the piston moves down, it pushes fluid out the bottom of the actuator. The fluid then passes through the valve in this direction on its way back to the reservoir. The piston can now move in one direction and one direction only, downward. To get the piston to move back up, the flow paths have to be reversed. Now we want the pressurized fluid to enter the bottom of the actuator and to push up on the piston. And we want the fluid to leave from the top of the actuator. This can be accomplished by sending a control signal to the directional control valve. The control signal causes the internal mechanism to move, shifting the flow paths inside the valve. Incoming and outgoing flow, in a sense, change places. Pressurized fluid is now directed to the bottom of the piston, while the fluid pushed out the top of the actuator returns to the reservoir. At the end of the piston's upward stroke, another control signal will reposition the directional control valve so the sequence can be repeated. Now, we can make this simple hydraulic system into a pneumatic system by making a number of relatively minor changes. We now have a compressor and receiver instead of a pump and reservoir. Compressed air from the receiver provides the fluid power for the system. There's a relief valve here on the discharge of the receiver to prevent the receiver from over-pressurizing. The symbols for both the relief valve and the directional control valve have also been altered slightly. This part of these symbols indicates a vent to atmosphere. In the hydraulic system, the fluid drained back to the reservoir. The basic operation of this pneumatic system, though, is the same. Compressed air is applied through the directional control valve to the upper side of the piston, forcing the piston down. Air under the piston is vented to atmosphere through the directional control valve. At this point, let's take a look at a different fluid power system schematic and apply to it what we've learned so far. This is the schematic for a hydraulic ram system. The ram is used to operate a crushing machine. The material to be crushed is placed here in the crusher. This system has a hydraulic reservoir indicated by this symbol. When the motor-driven pump is started, it pressurizes the system. The pressure relief valve maintains the proper system operating pressure. To activate the crusher actuator, this push button is used to send an electrical signal to the directional control valve. The signal causes the valving mechanism to move, allowing fluid to flow into the space above the piston. The pressurized fluid pushes the piston down. The speed of the piston is controlled by a variable flow control valve, shown by this symbol. This part of the symbol indicates a variable restriction. Adjusting the restriction controls how much fluid flows to the actuator and therefore how fast the piston moves. This is important because depending on the amount or type of material to be crushed, you might not want the piston to slam into the material. It might be better to crush it slowly. After the piston has fully extended in the crushing direction, a lever on the piston shaft trips an electrical switch called a limit switch. The limit switch causes the directional control valve to shift, repositioning the valving mechanism and causing fluid flow to be reversed. In this position, the fluid flows to the underside of the piston, forcing the piston upward. The fluid passing through the flow control valve does not have to flow through the restriction. It can flow through this check valve, allowing the piston to return to the top of its stroke quickly. The limit switch again trips, allowing the directional control valve to return to its original position. In this position, flow from the pump is returned to the reservoir. The piston is locked in place, and the crushed material can be removed safely. The systems that we've gone through in this segment on fluid power systems were very simple, but they illustrate the principles used in all fluid power systems. If you use the legends and follow the flow arrows, you should be able to read just about any fluid power print. Now stop the tape and review section 3 in your text. The last major type of mechanical print that we're going to cover in this tape is the machine print or equipment print. A machine print is a drawing of a piece of mechanical equipment or a part of that equipment. There are several different kinds of machine prints, different primarily in the kind of information that they're putting across. For example, there are detail prints, lubrication prints, maintenance prints, and assembly prints. Anytime you discuss the assembly, disassembly, or maintenance of a machine, you have to be aware of a key area. That is, you have to be able to recognize and understand the different methods used to fasten parts of a machine together. If you don't recognize and understand the various fasteners, you're going to have a difficult time assembling or disassembling a machine. Now, a word of warning here. There is a tremendous variation in the methods used by different manufacturers to represent a part or a machine in a machine print. Just as you did for piping prints and for fluid power prints, you need the manufacturer's legend for any machine print you use. Well, let's start with fasteners. We'll divide them into two major categories: fixed fasteners and moving part fasteners. Fixed fasteners are simply the methods of attaching non-moving parts to each other. The first fixed fastener we'll look at is probably the most familiar fastener to all of us, and that is the threaded fastener. We've all seen and used screws and bolts at some time or other. Let's see how they're represented in a print. A threaded fastener has a helix shape. A helix is the spiral shape that winds around the shaft of a threaded fastener and provides the holding ability of the fastener. There are many different thread types. This is a square thread, an acme thread, a knuckle thread. This is the American Standard thread. This is the crest, which is the top edge of the thread. The root, which is the bottom of the notch. The pitch, which is the distance between crests. The depth of the thread, and the thread angle. All right, now those are some of the thread types and some thread terminology. How are they drawn on a machine print? The helix shape of a thread can be either drawn in a pictorial fashion or it can be symbolized. It is drawn only when the print has the fastener as its main subject, and it must be drawn in its actual size or larger. For threaded fasteners that are drawn less than 1 inch in diameter on the print, the thread is usually symbolized. All threads are symbolized the same way. This is the American National Standards Institute, or ANSI, regular thread symbol. It is used to represent any thread type. The exact specifications of the fastener are written alongside the fastener or in an attached list. On the top is the top and side view of a nut or threaded hole. This is called an internal thread. On the bottom is the top and side view of a bolt. This is called an external thread. There is a second method of showing threads. It's called the ANSI simplified thread symbol. You can see that the thread representations on the bolt have been reduced to a dashed line. Again, exact dimensions are explained in a fastener specification number beside the part or on a parts list. Because the vital information on the type and size of a threaded fastener is frequently contained in a specification number, it's pretty necessary to be able to read the specification number. This is a thread specification number. It contains 5 pieces of information. Let's take them one at a time. This first number gives the diameter of the fastener. This number indicates a fastener with a diameter of 1/4 inch. This next number gives the pitch of the thread, expressed as threads per inch. This particular specification is indicating 18 threads per inch. The next part of the specification tells the thread type. This is a unified national coarse thread. This number can be only a 1, 2, 3, or a 4. Now, this number indicates the tolerance of the thread. That means, has the fastener been made to very fine specifications, or will it fit more loosely? In some types of work where speed of assembly is more important than tight fit, a thread with a number 1 tolerance might be used. Most threads, however, will have number 2 or number 3 tolerances. Number 3 is the most accurate, closest fitting thread. A number 4 thread is a specially made thread that is required to meet extremely exact specifications. You'll seldom find yourself using number 4 thread fasteners. The last piece of information you can obtain from this specification is in this letter. Very simply, A means an external thread, like a bolt, and B means an internal thread, like a nut. There are several other examples of threaded fastener specifications in your text. So now let's look at some of the fasteners themselves. A bolt is a piece of threaded metal stock with a head on one end. It's designed to pass through clearance holes in 2 or more aligned parts and then be tightly fastened with a nut. A flanged joint is a good example of using bolts. Bolts usually have square or 6-sided heads and are normally made to a number 2 tolerance or fitting. A cap screw is similar to a bolt in that it passes through a clearance hole, but then it threads into the bottom or last piece. Because the last piece has a threaded hole, the cap screw does not need a nut. Cap screws are usually a number 3 fitting. A stud is a piece of metal stock that is threaded on both ends. The stud is usually passed through a clearance hole in one piece of material and threaded into the second piece of material. A nut then holds the assembly together. Machine screws are like cap screws, except that they're generally smaller and they may or may not be used with a nut. They're usually a number 2 fitting and have a wide variety of heads. A set screw is much like a small stud, except that one end is shaped to allow the screw to be driven with a screwdriver or an Allen wrench. The other end is shaped to fit into a hole or depression in the second piece of material. The object of the set screw is to prevent movement between the 2 parts. These are the major threaded fixed fasteners. There are also non-threaded fixed fasteners. The 2 types of non-threaded fasteners we'll look at are rivets and welds. Rivets and welds are more permanent fasteners than the threaded fasteners, which are made to be easily removed. Rivets are used to fasten pieces together by being passed through a clearance hole in each piece, having the tail end deformed to create a tight hole. The rivet head provides the other end of the joint. Welding is a process that uses high temperatures to fuse 2 metals together. There are several varieties of welding processes and numerous different types of welded joints. The symbol for a weld joint on a machine is an arrow like this, pointing at the weld itself. This arrow just tells you that there is a weld. You have to add another symbol to the arrow to explain the kind of weld. This is a bead weld symbol, a fillet weld symbol, and a V-groove weld symbol. If the symbol is placed under the arrow, the weld is on the arrow side of the piece. If the symbol is placed over the arrow, the weld is on the other side of the piece. And if the symbol is both above and below the arrow, then there is a weld on both sides of the piece. Now, here are some of the more common weld joints with an appropriate symbol. This is a lap joint with a fillet weld. You can see the pieces overlap, and the symbol for the fillet weld is under the arrow, showing that the weld is here on the arrow side. This is a butt joint with a double square weld. In a butt joint, the 2 pieces are butted together. The weld is on both sides, so the square weld symbol is on both sides of the arrow. Anytime a weld is used on both sides of a piece, it is called a double. There are several more examples of different weld joints and other weld symbols in your text. We've been discussing fasteners that hold non-moving pieces together. Now let's take a look at some of the methods of fastening moving parts together. Pins are a good example of this type of fastener. Some pins are used in a tow bar and hitch arrangement in which the pin passes through the tongue of the hitch and secures it while allowing it side-to-side movement. Some pins are used in hinges, much as the pins in the hinges that hold the doors in your house. A common machine use of pins is as a locking device to hold two pieces of tubing together. We're all familiar with the cotter pin used in 100 applications like these. A cotter pin is often used to lock a hinge pin in place. Another moving part fastener is the key. Keys are used to prevent relative motion between parts. This is how a key does its job. The key fits into a key seat in one piece and a key way in the other piece simultaneously, locking the two parts into a specific arrangement. This sort of arrangement is normally used on a rotating shaft to lock another component to the shaft so that it turns with the shaft. There are several different types of keys and key slots. The key in this picture is a square or rectangular key. This key is called a gib head key. Keys are usually identified on drawings with an arrow pointing to them and a note specifying the type and size of key. Another type of moving fastener is the common spring. A spring actually stores energy when it's twisted, pulled, or compressed. These are three common types of springs. Each has its own symbol. This is a regular compression spring. When it is compressed, it tends to spring back to its original position. This is a tension spring. When it is stretched out, it tends to return to its compressed position. This is a torsion spring. The torsion spring tends to return to its original position when it has been twisted. Threaded fasteners, rivets, welds, keys, these are all methods of attaching or fastening pieces of equipment together. Okay, now let's look at some of the different types of machine prints. A set of detail prints will describe the individual parts of a machine. Each print will provide enough information to fabricate the part if necessary. Included in this information will be all dimensions, the type of metal used, the fabricating process used, and any special processes or requirements that must be followed. An assembly print can be any of a number of different prints whose objective is to make it clear just how to assemble a machine. In a set of assembly prints, there will usually be sub-assembly prints that explain how parts of the machine must be assembled. An assembly print may often omit dimensions or materials because the point of an assembly print is to show how the parts of the machine fit together and what holds them together. A cutaway is used to clarify a piece of equipment or how a part operates. Remember that a pictorial drawing is often used this way to complement a symbolic representation. This is an exploded pictorial. It is used primarily as an assembly print. It's very effective at making the relationship between parts very clear and easy to understand. Machine prints encompass a lot of different kinds of prints. We've discussed a few of them. The key point to remember is to use the manufacturer's legends whenever you're dealing with a machine print. Now, stop the tape and review section 4 of your text. In the next segment, we'll discuss a method for approaching any type of mechanical print. We've looked at 3 different types of prints: the piping system print, the fluid power system print, and the machine print. Now, let's develop some rules and guidelines for successfully reading a print, any print. When you pick up a print to study it, it's going to be for one of 2 reasons. Either you're learning the operation of a system or a machine, or there's something wrong with the system and you need to read the print to troubleshoot it. If you're using the print to aid in troubleshooting the system, there are 4 positive steps that you should take to ensure that you're getting the most out of the print. The more information that you get out of a print, the more it'll aid you in the troubleshooting. Now, these 4 steps are a method for successful print reading. First, use the print to gain a firm understanding of the system or equipment and what is supposed to be happening. Second, use the print and any other information you have to determine exactly what is happening, what's wrong. Third, using the print, draw up a list of the possible causes for what is happening. And fourth, investigate the possible causes until you've found the true cause. Now, let's take these 4 steps one at a time and troubleshoot a problem in this system, a fairly simple cooling water system. Step 1 is to find out how the system is supposed to be operating. Now, there's a great deal of information that can go into this step. Before you even start to read the print itself, there's other information that can be obtained. For instance, look at the title block on the print. This title block contains a lot of information that can help you read the print, such as if the print is a plant system print, the name of your plant will go here. If the print is a machine print, this will be the name of the manufacturer. Knowing who the manufacturer is can help you with symbols and line conventions. If there is no legend on the print, you may be able to go to another print by the same manufacturer to find a legend. Now, if the print is of a machine part or a component in a system, you will probably see it listed with the name of the part and the name of the system to which it belongs underneath or beside it. Now, the print number here will tell you if this particular print is one of a group of prints. This block indicates any revisions that have been made to the print. Over the years, as manufacturers change and improve their products, they'll issue revised prints to reflect the changes. Different types of prints will have different information in the title block. For example, a detail print of a machine part might contain the material the part is made of and the tolerances that can be allowed if the part is to be refabricated. All prints will have the information we just covered: the manufacturer or the name of the plant, the name of the system, machine, or parts, the date the print was drafted, and the print number. After checking the information block, get out the manufacturer's manual for the machine, or the system description if the print is of a system. The manual or the system description should have sections that will take you through the operation that the print represents. There are 4 pieces of information that can quickly show you the flow paths through the system. The most obvious of these pieces of information are the flow arrows. All too often, however, you find prints that don't have flow arrows, like this, but there are still other indications of flow. For instance, pumps and compressors take a suction from one direction and discharge to another direction. In this case, the shape of the symbol for the pumps helps to show which direction the discharge is. But if the symbol were to be a simple square or circle, basic engineering practices tell us that we throttle the flow from a pump at the discharge of the pump. So, if we look for a throttling valve, a globe valve, we know that is the discharge end of the pump. Now, there's another valve that'll show the direction of flow through a system, the check valve. In this check valve, the slanting line indicates a disc inside the check valve that lifts to allow flow in this direction, but will seat to prevent flow in this direction. There may be a small black dot to indicate the hinge on the disc, also indicating that the flow comes from this direction. Another piece of information that will help determine flow paths is the line convention used in the print. In this print, these pipes do not join, so flow cannot branch off in this direction. Once you know how the fluid in a system is supposed to flow, you should have a good grasp on what the system does. Now, the next step is to determine what is really going on. You know what's supposed to be happening. Now, what is really happening? This sort of information will normally come from the operators of the machinery that is connected to the system. In this example, let's assume that the operators have found that a heat exchanger off of this line is not getting enough cooling water, with the result that a machine is running too hot. The third step in our print reading method is to determine the different possible causes for this problem and to list those causes in order of greatest possibility. The most effective way to do this is to trace the line from the machine back to the beginning of the system. The first component we run into is a manually operated globe valve. This valve is used to throttle the flow to the piece of machinery. If it were not open far enough, it could prevent the machine from getting its proper cooling flow. The next component is a check valve. If the check valve disc is stuck in a partially closed position, the cooling water flow through the valve might not be enough to supply proper cooling to the machine. Next in line is a heat exchanger. If the heat exchanger were not doing its job properly, then the hot running machine may be getting all the cooling water it is supposed to get, but it just may not be cool enough to cool off the machine. We next have a strainer to strain out particles in the water that might foul up the system. If this strainer were clogged up with debris, it might not allow enough cooling water flow to the rest of the system. We have a set of strainer isolation valves, another check valve, the pump outlet throttle valve, and the pump itself. We've already mentioned the possibilities of a valve being out of position. What about the pump? If the pump isn't putting out enough water, it could be for a couple of reasons. The discharge might be throttled too much. The suction valve might not be fully open. Or the pump suction head might be too low. If the level in this head tank gets too low, the pump will not operate properly and it will not put out enough flow. So there are a lot of possible causes for that machine not being cooled properly. The last step in our method is to investigate all of these possibilities until the correct problem is found. Most of these possibilities are fairly easy to check. The level in the head tank can be checked. But if the other pump is running properly, it's doubtful that this is the problem. All of the rest of the possibilities can be just as easily checked. Is the pump suction valve open? Is the pump discharge valve open to the correct position? Are any isolation valves shut in the main line? Or are any of the check valves in the main line stuck? Is the differential pressure reading across the strainer too high, indicating a blocked strainer? Are the cold water valves open to the proper position to cool the cooling water? But all of these possibilities can be checked in one step by checking for proper cooling flow at the other branch connections. If the components off these three branches are getting proper cooling, then it is not likely that the problem is anywhere in this part of the system. That leaves this portion of the system.